welcome to another week. So, yeah, what I will do is I will go through assignment 3 first, and then we can quickly duck back to assignment 2 for any questions in regards to that. To start off with, assignment 3 drawings are up here. They differ slightly, well, they differ actually substantially, I guess, from some of the drawings that are shown as examples within the assignment text, but this is a much better building to work from than the other drawings I had initially with the assignment. So I've decided to go with this. So what we have just a concept SketchUp drawing initially to get an idea of the building there. So we've got a 3-story commercial building with retail showroom at the bottom and then office accommodation at the top. Automatically that should get you guys thinking, okay, possible multiple classification here of building. We have a site plan showing the building and its surrounds. Not really pertinent to your assignment, but useful information, interesting information. Floor plan of the lower retail showroom. Fully dimensioned floor plan and fully annotated floor plan. You can zoom into that, see that in a bit more detail if you wish. Have all of you done working drawings yet? Or have any of you done working drawings yet? No? Is that that's no's. Right. So this is probably, I guess, a really good start for you guys to have a look at this, have a look at how it was created and get an idea of your working drawing. So this is for the assignment, but it's actually a really good example of a set of working drawings for a commercial building. And if you have any queries about what all these things mean, by all means, ask me about them. I guess we can go through a few things just very quickly, not that it's at all pertinent to the assignment, but these A, B, C, D, E, F, G, H, I, J are what we call grid lines. So we've got our alphabetical grid lines from left to right and our numerical grid lines in a vertical fashion. That enables us to identify structural elements and see the layout of a structure and convey that layout of a structure clearly between drawings. So what we can do is, with this floor plan here, through every structural element, so we have the end walls, so end wall A, B, and C, we have a grid line for those. And then we have dimensions for the center points of those walls that creates our grid. And then from there, other important structural elements are our columns. So we have columns, center points in line with grid line C, center points in these columns in line with grid line D, etc., 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 all the way through. Now, what I could then do with this is take away this building, and if we want to do a footings plan, we know that the center point of our footings to support this column at D5 is at that dimension of D5. So it makes that the structural elements easily transferable between the floor levels. Does that make sense as to what that's used for? These are section indicators. That is not necessarily how I would typically, when I have section indicators, I use much bolder font and much simpler referencing as well. So they've got section A and then a numerical reference, and I'm not exactly sure what that relates to. That's all about confusing. So I would have, it should relate to the page, but a page of A190815-300, not so sure what that relates to. So typically I would have section A, and then I would have page reference under that, which would be SD1 or SD2. So I would, SD would stand for structural detail page 1, structural detail page 2. So
Yeah, that's page number. If you refer to that number there, that's a single, that's the same.
Which number? This number here?
Yes, that's page number.
Page number, right.
So if you
okay, get right down to the bottom here.
It actually says page number, doesn't it?
Yeah. Okay, yeah, so they have, yeah, so, yeah, that's not how I would do it myself, because that's only going to be legible at, you know, on an A1 drawing, you know, on a large scale. In fact, it's not all that legible. I prefer to number my pages D1, D2, D3, D4, D5, etc. like that, and then so that's drawing 1, 2, 3, 4, 5 through to the end of the drawings, and then if I have any plan details, I will have those page numbers as PD1, PD2, PD3, and section details SD1, SD2, SD3, etc. And sometimes when we have plans for both architectural drawings and then for structural drawings, I'll have it AD1, etc., and then have SD1 for the structural drawings. And then if I have section details, then I would change that. But yeah, anyhow, that's a preference. I prefer to keep things very clear and very simple on drawings. Also, another thing about drawings should always be read in conjunction with a schedule of works or specification. And so, knowing that, you should keep your drawings as clear and as simple as possible, and all the lengthy wording goes into the specification. So, I would have, you know, if I wanted to talk about this lift, I would have lift as per, and then give a reference within the specification to talk about the type of lift and the manufacturer of lift and the interior fit out and finishes, etc. Anyhow, that's digressing just a little bit. But these are apart from that fiddly detail there, I think these are excellent plans to use as a guide and as a reference to get to know what you should be including on your plans for when you are doing working drawings. You'll start off with your working drawings doing something much simpler than this, by the way. Also, just a quick note about reading dimensions. So, the closer the line of dimensions, so here we have 1, 2, 3, 4, 5 lines of dimensions, excluding our grid lines. These dimensions back here, the first one relates to, so we got 265 here, and then we have a large space to a 90 wall there. So this set of dimension lines relates to this plane cut straight through the building. The next one should relate to further out. So the next one relates to this wall here, and then that wall again, etc. And then as we move out, we also move further out on here. So we've got dimensions that relate to this wall here, like that, and then we have an overall dimension. And that's the way dimensions should always be set out, and that's the way that they should be read as well. So in case you wanted to get some information to interpret those dimensions, that's how we go about doing that. And for this assignment, you will have to do that as well. So you're going to have to calculate floor areas. In the example given in the assignment, it says 250 square meters of floor area. Now that's not significantly different from the answer you should come up with here, but it is slightly different. So I can see who's calculated the floor area and who hasn't. That can be done by just simple maths, by multiplying, you know, this dimension by that dimension and minusing this area, or you know, or however you wish to approach that. So we have our lower floor, ground floor plan, our first floor plan. So it shows a large open office space with open kitchens at either end, an enclosed server room, and enclosed toilets.
triangles with a W3 or whatever.
That's to denote the wall type. So wall 1, wall 2, wall 3, wall 1 again, and wall 2, which is masonry wall. Actually, what's not on here though, interestingly enough, are elevation indicators. And typically I would use a symbol similar to this to indicate the elevation as well. So I'd have just an arrow at number 1 and then a page reference under that. But that's okay. It's fairly easy to discern which elevation is which further down, and they're not pertinent to the assignment. And then we have third floor plan as well. Similar layout and plan to second floor. So that's fairly simple. And then further on, we've got a roof plan. That's going to be important to you because within the assignment you have to calculate how many photovoltaic panels you can get onto that roof. So we've got panels of 750 wide by 1500 long. They have to be, and I'll just quickly draw it diagrammatically on the board here. The way we have to set out our panels on the roof, but this is all explained within the assignment literature. Let's say we've got our roof looking like this. With our banks of panels, we need to have 600mm offset from the outside walls. So this is all for access. So 600 here, 600 here, that. So our first panel has to be in there like that. And then we can only put them together at banks of 2 before we need another 600mm offset from that bank to another bank for access around. But we can create that bank all the way along until 600mm from there, and all the way along like that. And then so it's just a matter of dividing that up by 750mm all the way along, and we get X number of panels in there. And then the same thing here. We need 600mm offset between those two, and then 600mm there, or possibly we can get a third bank of panels in there. That's for you to calculate. So what we have to play with are rectangles that are 750mm by 1.5 metres or 1500mm, and they can be in banks of 2, and between each bank of 2 we need that 600mm difference, but we can rotate these any way we want. So they can be in that vertical, so in portrait view or in landscape, they can be set out either way. So I might do a section of them here in portrait, but then here I'll do some in landscape, because that I can fit a couple in like that, and I keep them, run that bank down to there, for example. And then this one might also be in landscape or in portrait. It depends. So that's for you guys to work out and muck around with. From this assignment last semester, I got almost as many answers as I had students as to how many panels you can fit on there. But in the main, they were all pretty much around ballpark. So there was just some, a few. Just I guess being so many different ways you can lay panels out, etc. Some people were able to squeeze a couple more panels on there than other people. But the fundament is that you can only have 2 of them together, because we can't have 3 of them together, because otherwise we can't reach in there to service them or clean them or get under them. But look, so because I got a whole bunch of different answers around the same figure, look, I won't penalise people for getting the wrong answer, or less than what I can get. What's that?
As long as you can show how you've done it or how you can
yeah. But it's just a bit of a fun thing to work. It's a bit like Tetris or so to work out. What's that?
Way more fun than that.
Yeah, solar panel Tetris on the roof. Yeah. So see how many you can fit on there. And so we have elevations here. That's showing curtain wall glazing. So we've got our different curtain wall panels there, curtain wall 2 and curtain wall 1, etc. And then our rear elevation showing the masonry wall and the balcony and further curtain wall glazing to the right hand side, and then our end elevations here, so east and west. And we have a section and this is not pertinent to the assignment, but once again, really good good reference point for you guys for doing working drawings. See how other people do them, and then some plan details here. So it shows our column wall junctions, etc. And this is of a typical standard that you'd normally see in a professional setting. Although certainly with these details here, there's basically no annotation. The purpose of showing such details, typically in a professional sense, is to be able to annotate what we have going on there. So normally, if I was to do these drawings, I'd have maybe a dozen levers poking off various different bits here. We have a stair detail or stair section. So that's it for our drawing. So, but the main point we take away from that is we've got a 3-story building. Lower floor is retail. Upper 2 floors are office. Oh, right back to here. That's interesting. So now on to the assignment 3 text, the task requirements. Apologies for not updating this date on here, but you all have the due date. I've got it here in the diary. In November, we've got so I've got Monday 20th assignment 3 due 5 PM Monday the 20th of November. So that gives 3 days for any resubmissions, etc. before close of grade, before everything has to begin. So there's not a great deal of time for reworking things, but there's a few days. So task requirements, so this will be very familiar. So for this task, you're required to provide a report comparing and evaluating structural and cladding and service options plural, for a 3-story office building. Include a reference to all websites, manufacturers' guides, and other sources of information at the end of the project. So please keep track of where you sourced your information from. So research and evaluate structural and cladding systems for the low-pitch roof. So it's a flat roof with a parapet wall. So think about possible structures for that. In the drawings, they had low-pitch trusses in there. That may be the way to go, or there may be another way to go. Walls may be a mix of load-bearing walls such as concrete panels, concrete blocks, and non-load-bearing walls with columns such as glazed curtain walls, and lightweight cladding options such as loop bond, press fibre cement sheet, etc. So you'll see that the building does have structural columns, and there's the capacity for the non-load-bearing walls on several, if not all, elevations. Also, suspended floor system for level 1 and level 2. Refer to the guide for long-span concrete floors. So, yeah, possibly cast in situ concrete floors, or it may be precast concrete floors, or it may be Hebel flooring, or we may have another flooring option that's not concrete or cementitious based. Now, this VCA requirements should also be fairly familiar to assignment 2, but we'll go into that right now because we have a reference to this this in assignment 2 as well. So, according to BCA Part A 3.2, what class of building is it? So fine. Actually, could anybody tell me a quick pop quiz what class of building it is? How do I get this out of the way? I was just wanting to get to our top tabs here. G'day. It's majorly annoying. No. Maybe I can drag that down. Okay, so what I've got up here, already logged myself into the BCA a little bit earlier on, so we can save a bit of time. So I'm here right now, and we've got. I do want this nice and large, so I'll maximise it again. So this is the National Construction Code in PDF form or online form. We've got our contents down the side here. So it asked for what is our building classification. So we go section A, general provisions, because it was section A 3.2. Click on the arrow there to bring down all your subheadings. We've got part A3, classification of buildings, and blah, blah, blah. I reckon that sounds like exactly what we want. A3.2, classifications. Let's go there. So just click on that, take us there. All right, so talks about what class 1 is, class 2, etc. I'm going to save the suspense and get onto this. I know that it's a class 5, an office building used for professional and commercial purposes, excluding buildings of class 6, 7, or 8, or 9. So our upper floor, that's a class 5. But we've got here, class 6, a shop or other building for the sale of goods by retail or supply of services direct to the public. That's what our lower level sounds like. So this is assignment 3, by the way, can you hear me? Yeah. So this is the next building on. And yeah, what I showed before you came in was a floor plan of the building for assignment 3, which is a 3-story building with retail at the bottom and then offices at the top. But we're going through the BCA like we did last week with you. So we have a building there which is of multiple classification. Now, what we can do is if we wish, we can go in here, where is it? Acceptance, I think it's under acceptance. Anyhow, there is, A 3.3, multiple classification. Let's find out what happens when we've got multiple classification. So each part of the building must be classified separately, and where parts have a different purpose, not more than 10% of the floor area of the story. B, being the minor use is used for purpose of different classification. Classification applying to the majority use may apply to the whole story. That's fine, but it's not relevant to us. Provisions do not apply with minor use. Yeah, plant room, machinery room, same classification. That's parts with more than one classification. We're not. What I was hoping to get to was possibly it's in fire resistance under that. It says, so when we go for attributing fire rating levels to all the walls, it says for buildings with multiple classifications, you must adopt the more stringent of the fire ratings of any of those classifications. So we've got 5 and we've got 6, and we have to adopt the more stringent of those classifications, which by the way will be number 6. So there doesn't help us too much with what we're looking for. So we know that it's class 5 and class 6. Then what the assignment asks for, so we'll just quickly look back to that again. Oh, that's a different page, sorry. got.
First one.
I'm going to click there. Yeah, but then I'm going to have these issues of this bar being the way which I can't move around. But then so according to BCA Part A 3.2, what class of building is it? Okay, so we know it's 5 and 6. What type of building is it defined in the BCA? Part C1 in table C1.1. So we'll go have a look at that. No, because it's hidden behind this bar. That's the issue, and I can only slide this bar sideways. Yeah. Yeah. Okay. Alright, so what we want to do is want to go to section C for fire resistance. So drop that down, and then C1.1, type of construction required. So in our table C1.1, type of construction required, we're able to get that. So we have rise and stories. We have 3 stories. We have the ground floor, and the first floor, and the second floor. So we've got 3 stories. In class of building, we're class 5 and class 6. That means we're type B construction. Then the assignment asks us for what are the fire rating levels for various different walls, etc., within specification C1.1. So what we can do is we can just use this hyperlink here and click on that, specification C1.1, or we can go down here, part C specs, specifications, get that drop down arrow, specification C1.1, fire resistant construction.
That's always the confusion most times. Because when you go through, like now, it's that one now is like under part, is it part C2?
Yes. Yeah.
So it gets confusing
It
because
does.
we're already in part C1.
Yeah. Yeah.
So you just think maybe you're going to somewhere else. So that's the struggle.
It is.
I tried it the last time. It's so confusing.
It is incredibly confusing. But unfortunately, that's what we have to deal with. I can't help you out any more than that. Apart from what we have part C1.1,
Yeah.
and then we have the specifications that relate to that. So we have that, and then we have another specifications like an annexure to that section. So this section up here refers to our specification. So all we have to do is remember that the information we want is actually within the specification.
Okay.
Because what we have, so we have type of construction required. The minimum type of fire resisting construction of building must be that specified in table C1.1, which so table C1.1 is here, and specification C1.1. And then you end up cruising around here like a headless chicken looking for specification 1.1. But the best way to get there is just to click on the button.
Okay.
So we click on that, and I'm glad it didn't make a fool of me. So this is some good bedtime reading if you want to get to sleep really well. But what we're really looking for is this type A fire resisting construction. But we're not type A, we're type B. So let's keep moving on. And then type B, fire resisting construction. So that's the one we want. Now, this may be of pertinent reading, but specifically for the assignment, it's asking some specific questions that can be answered from this table here. So we're type B, we are class 5 and class 6. So we have to go for the worst and the most stringent. So we have to go for class 6. So that's 100. So for load-bearing parts less than 1.5 meters from the external boundary of the building, it must have a fire rating of 180, 180, 180. And so, yeah.
So less than
from any fire source feature to which it is exposed. But what that also relates to is the wall. So if the building is built right on the boundary and you have a window within 1.5 metres, or you have, for your wall, that 1.5 metres right from the boundary, even if that's a vacant allotment next to you, that is still a fire source feature because we don't know what's going to be built
next to
that, and whether they're going to build right on the boundary as well. So if we are right on the boundary, that's a fire source feature, whether there's another building there or not.
So what does that really represent? Sorry, if that says 180 by 180 by 180. What does that really mean?
Yeah.
Like,
so that's time in minutes.
Yeah.
So it has to. So 180 is so up here structural adequacy.
Yeah.
So if there's a fire happening there, it has to stay up and has to be able to hold the building correctly for 180 minutes.
Okay.
So for 3 hours.
Yeah.
And it also has to not lose its integrity. When we talk about integrity, that's about getting holes in it or being able to let fire into it. So for 3 hours, with a fire burning right there, it has to not fall apart.
Okay.
And then insulation. So it has to stop the transference of heat from the outside to, exactly. And within the National Construction Code, there references Australian standards on how to test that insulation, what amount of heat is able to pass there, but that's not, that's for people who are engineering systems.
Okay.
For us, we have to choose proprietary systems which adhere to this. So we go, okay, this Hardy system achieves 180, 180, 180, that's fine, that's what we need to do. Where you see just dashed lines means there are no requirements for that section. So once we get 18 metres away from a fire source feature, it doesn't have to be designed to withstand fire for 3 hours in any sense.
If you've got a dwelling, you've got multiple dwellings in this dwelling, so that's between each dwelling.
Yep.
So if you're an 8 metre wide building that starts at 0 every time you go one unit to another.
Yes,
So that means each one of your walls then is going to comply with that. One or two.
Yes, so your multiple dwellings are going to be in 2 or 3, and going to comply with those. Now they are less stringent than your retail, for example. And so this is where you'll find all of your answers for that section there. But you should also be able to understand this for assignment 2 as well. So this section is important for assignment 2 as well.
So does it mean that this table applies to both the floor, roof, suspended floor, the roof, and the walls? On the same table.
Yes. So we have external wall.
Yeah.
We have external column walls, and internal walls.
Yeah.
Here. Other load bearing columns and roofs. And in regards, I'm not sure exactly where it is. There's not a section for floors, but what there is a comment. Now it's a comment buried in here somewhere that says the floor.
The floor part must have to be FRL 60.
Yeah. Or that's stair shaft supports any floor, but here it's the underside of floor next above if that floor has an FRL. No. Anyhow, floors should always have a fire rating level of 30, 30, 30, or what the fire rating level of the internal walls are for that classification. Now that comment is buried in here. I won't find it. Okay, so no, that's class 19. Yeah, no, it will take me a while to read through here to find it. So in class 5, 6, 7, 8. So that's what we are. Class 5. No, that's the shafts. But anyhow, that comment is buried in here that the floors need to have an FRL of 30, 30, 30. I won't flick through, look for that right now. Yeah, but we have for the specific questions on there, you should find all those answers within that table.
Okay.
But yes, for both assignment 2 and assignment 3, because we are dealing with floors separating areas, we need to have that FRL of 30, 30, 30 for all of those floors. Okay. So this should be fairly familiar. So for structural elements, research the following aspects of at least 2 different materials different from previous tasks. So material properties, fire resistance properties, coatings required, distance required, etc., etc. This should not be all that new. And then cladding, research and evaluate 2 different wall cladding systems, different from task 1 and task 2, possibly a loop bond, curtain wall, concrete panels, compressed panels, and sheeting, damper on concrete masonry, or other. Yes, you can confirm with me, but I haven't really had any really silly requests yet, so that's fine. I trust you to press on. For each wall cladding system, consider the following advantages and disadvantages of each cladding options, limitations, size, applications, environmental impacts, thermal properties, and which Australian standards apply. So that's all fairly similar to assignment 1, assignment 2, and also this note is included in both assignments as well, where pertinent include structural details of building systems chosen, etc.
So to that last question there, to which Australian standard applies to the material?
Yeah.
Does that mean that you have to go to the BCA as well, or?
Yes, you can. Yes, so you can. So you can go to the. You can go through the BCA. So so we can find out what Australian standard applies, or we can. Well, typically you can actually just Google it and go, okay, Australian standard, brick veneer or brickwork or whatever, glazing, whatever, and you will come up with all the relevant Australian standards for that. But also, possibly the best location to go for that is the SAI Global website. And they are the people that host all of the Australian standards. And there you can search the Australian standards for whatever you want for any of these materials. But typically a quick search is going to tell you what the relevant Australian standard is, because there is so much information on the internet about Australian and New Zealand standards. And so, but the meat of this assignment, so that should all be fairly familiar from assignment 1, assignment 2. The process and what we need to do. It's just now in a multi-story commercial context. However, the meat of this assignment is within services. So see Moodle for all details and resources to complete this section. So let's head back to Moodle. under 3-story commercial, right down the bottom here, we have task 3 energy. So we have a PDF here, and then we also have an Excel calculator. Now, does everybody have Excel on their computers at home? Have access to Excel spreadsheets?
Yeah, I think Word documents.
Yeah.
Word documents. That's right.
Yeah.
Word you most likely have.
Yeah, you most likely have Excel.
Greetings.
Yeah. So, yeah. So this is it. Have you used Excel before?
A long time ago, when I was doing estimate, I think something like that.
Yeah. Yeah.
Material estimate.
Yes. Yeah. So you use a spreadsheet application like this for estimating. What this spreadsheet has been set up for doing an energy analysis. So what we can do is all these squares that are in yellow, we can put figures in here. So 70, and that is going to change our outcomes. So I've just put 70 air conditioners in this building. They're the efficient ones, so we've got all our watt ratings, so 35 watts on 8 hours a day, etc. So that's all set. But all of a sudden, by putting 70 air conditioners in is going to cost us $1,682 a year to run. So that's how this Excel spreadsheet is set up. And so any of these yellow cells we can change. So what the assignment asks you to do is calculate all these, or come up with scenarios or numbers for this Excel spreadsheet for saying this is how, if we use inefficient appliances, this is what it's going to cost us per year. Or if we use efficient appliances, and this is what it's going to cost us per year. So close that down. So that's our Excel spreadsheet. So you'll have to fill that out, but the way we go about filling that out is by going through this whole PDF. So, and it's presented here as a presentation, but it's also part of the assignment. So this presentation is a brief introduction to electrical power consumption. Following topics we covered: electrical energy, lighting, air conditioning, computers, and refrigerators. So electrical energy is measured in watts. Electricity bills charged for every kilowatt hour used, expressed as kWh. So 1,000 watts used for 1 hour equals 1 kilowatt hour. So lighting and power consumption. Most electrical products will have power consumption expressed in watts. So typically you look at the back of the appliance and it will say 1500 watts if it's a radiant heater room. So, well, here we go, a light load rated at 100 watts. If you leave that light on for 10 hours, it will use 1,000 watts. So 100 watts by 10 hours equals 1,000 watts, or that's 1 kilowatt hour we just used. And typically, the greater the wattage, the greater the light output from that light. We measure that light in what's called lumens. So I don't know if any of you, when you're shopping for light globes at the supermarket, when you're going through and looking at all your lumens, I'd possibly spend too much time on that. I'm trying to get most lumens per watt per dollar for my light globes. So the amount of light emitted from the globe is measured in lumens. An efficient lamp provides the same amount of lumens, so light levels with less energy, less watts compared to an inefficient lamp. So here we go. Here's a chart showing what sort of lumens we can expect from each light source. I'll try to put that in the divided Okay, so this is our standard incandescent light globes, which are getting pretty rare. So the 40 watt incandescent light globe is going to produce around 450 lumens. A halogen light globe, which looks very similar to an incandescent, uses 29 watts to produce those 450 lumens. A compact fluorescent uses about 10 watts to produce that 450, and a 5 watt LED will produce 450 lumens. So here we are. This light globe for the same lumens is using 1/8 of the power of the incandescent light globe. And so 100 watts to produce 600 lumens has only 19 watts from LED. Get that screen. Right. So as with anything in building, there is an Australian standard for it. An Australian standard for workplace lighting. So yeah, I guess essentially our disclaimer here is saying lighting is a specialised field and a lighting designer should be consulted when specifying light selection, because it is quite complicated. But if we were to break it down into being simple, which is what we're going to do in this, you can come away and do at least this exercise. So there are many factors determining the choice of appropriate lighting. Colour, temperature of light, warm or cool. So that has to do with the frequency of the light waves emitted from that light source. So our LEDs and our compact fluorescents, they give up a cool light. So there are a lot of blues in that, whereas our incandescent give up warm light. So there's a lot of yellows and oranges within that light. So it's a different spectrum of light. So that's concerning consideration. However, there are a lot of very efficient light globes now that are able to produce warm light. So colour contrast and reflectance of desktops. So if we have a lot of reflective surfaces, we can reduce the lumens required for a room. Brightness of other surfaces such as walls and ceiling. Glare. Distance between the globe and the surface it is illuminating. So if I've got the globe a couple meters higher there, it's going to give me more light than if it's like 5 or 6 meters high. We lose efficiency as we move that light source further away. Also, the lighting required is going to be dictated by the tasks being performed. If I'm a jeweller and I'm working with expensive diamonds, etc., at a minute light level, I'm going to want a lot more lighting into that space and direct lighting than I would say if it were a romantic restaurant. So here is an extract from the Australian Standard. So according to the Australian Standard 1681, ordinary or moderately easy office tasks, the illumination required is 240 lux. So our actually we haven't the slides haven't explained yet what lux is. So lux is the amount of light at the working surface. So the globes are producing lumens, and that's how we measure that light coming out. It's coming out as lumens. But on my work surface, it's talked about as lux. So with, let's say, the light source there, which is 2 meters away, it will produce 0.8 lux for every lumen that's emitted from that light source feature. And then as I move that light source feature further away, let's say it's 4 meters away, it produces 0.4 or 0.6 lux for every lumen which is produced, or even further away, 0.2 lux for every lumen which is produced.
The distance depends on the watts.
Yeah, so we have watts, which is how much electricity the light globe uses, and then the light that it gives out. So I'll try to draw it diagrammatically actually. So that light globe,
Yeah.
right, going in there is watts. So that's the amount of electricity going in there. Coming out is lumens. Those lumens travel through space and hit the surface. At that surface, it is lux. Now, let's say I'm producing 100 lumens out of this light globe, but because of my distance here, that light is starting to get refracted, so it's starting to get sent off in, any particles getting sent off in all directions, so it's not as efficient. So if my work surface was right there on the globe, for every lumen, it would be, so 1 lumen, 1 lux, so my lux measurement here would be 100. But as I get further away from that, let's say it's 2 meters or so, my lux is going to be 80. Another 2 meters, it's going to be 60, etc. 40 lumens, because we get less and less efficient. So 60 lux and 40 lux, like that.
It's basically lumens per square meter.
Yes.
Lumens per square meter.
I'm not sure that it's measured per square meter. Is it per square meter? It is, right, is it? Yeah, so it's lumens per square meter, but yeah.
Because the distance is what is calculated from. So
Yes, but
the farther the light globe,
yeah,
The lesser lux.
the lesser lux you
the
don't.
lesser lux.
Okay.
Yeah. And so, yes, there is a formula. Yeah. So recommended maintain luminance lux at the work surface for easy visual tasks with high contrast and light detail, we're at 240. So for the intensive assignment, we require 240 lux at the work surface. And this is the formula for calculating that. So we need to provide illumination of 240 lux, but this does not equate to the lumen output of the lamps. The intensity of light diminishes over distance. The level of light that hits the desktop is not the same level that is emitted, etc., as some light is lost. To determine how many lumens our light fittings need to provide, we need to use the calculating illumination formula, which is this formula. So it's illumination in lux equals lumens per lamp times by the coefficient of utilization multiplied by the light loss factor divided by area per lamp in square meters. So we then get our equation. So illumination, we need that to be 240 lux equals our lumens per lamp. So sorry, that's behind a divider there, but that's one thing we don't know yet. That's what we want to find out. Multiplied by 0.6, so our coefficient of utilization, multiplied by 0.8, which is our light loss factor, divided by 250 square meters, because we've got a 250 square meter office space. So, for the purposes of the assignment, use these figures. So we've got 0.6 and 0.8 for our coefficient of utilization and light loss factor.
So where to find the coefficient and the light loss factor?
I do not know.
But expect
Yes, or specified within the Australian standard.
It depends on a lot of parameters.
Sorry?
It depends on a lot of parameters about the light fitting and the environmental effect, even the colors of the walls and everything.
Yeah.
It's not easy to find.
So how?
You need to get that one from
From a lighting designer,
that's right.
or
Yes.
but so
But basically, you can get something like light loss factor, something like 0.8, and the other one
coefficient of
is
utilization.
that's same, falling in between 0.5 to 0.7 like that.
Mm-hmm.
It depends on the fittings you're using. You know, the light loss factor is basically, if you're using a brand new light fitting, by the time it get corroded, maybe the reflectors getting corroded and some dust covering,
Yes.
then we can't get the same light levels from that fitting. Then we have to keep some tolerance. Then we're going to get that, instead of having 1, we're going to use 0.8. But you don't get that the same light levels in a period of some time.
Yeah.
Then exactly, there are so many parameters to consider.
Cool. Thank you for that.
It's not easy to find that
No.
loss factor and yes, coefficient of utilization.
Yeah. But obviously, I can't use those
Yes.
same numbers
Probably.
for every situation.
Yes.
So
No.
then I have to know what
No.
I can look it up.
And hence the caveat of a page up: lighting is a specialised field, and lighting designer should be consulted with specified light selections. But this is just a bit of a snapshot
Yes.
of, to give you a bit of an idea of what goes into there. But thanks to Sean, but you've got a bit more detailed knowledge about this than I have, so by all means pipe up. Yeah, thank you. So through some algebraic gymnastics, we can isolate L, which is the figure we want, so the lumens per lamp. We want to know how powerful our lights need to be, basically. So by algebra, we can say L equals 250 times 250 divided by 0.48. So 250 square meters.
Yep.
So 250 square meters. The house, although 250 lux. Yeah, it should be 240. Yeah. So 250 by 240 divided by 0.48. So there's an error in there. And that gives us 125,000 lumens are required to get 240 lux at the desktop. We need 125,000 lumens for that 250 square meter area. And so if there are 30 light fittings, you would need 4,340 lumens for each light. So we'd have to find light fittings that produce 4,340 lumens.
So the area is area per lamp. 250 square meters. In the form
So-
on the left hand side.
Left-hand side here.
Down the bottom, so area per lamp.
Yeah. So
250 square meters.
so that's
total area of floor space.
so that's the total area of floor space.
Right,
So because we're trying to work out how many lumens total we need.
Correct. So that
So-
should be total area.
Yeah, so that should be total area. Yeah.
Okay, so you work out the total area of the space.
Yep. Yeah. So
That's what we need to work it out.
yeah, so we need to work out the total area of the space, or you also need to work it out for air conditioning as well. So we work it out for lighting, and although you're going to get different figures for lighting and air conditioning, because you have workspaces which need to be lit, whereas other spaces that are that don't need to be lit to 240 lux, so they're not workspaces, they can just be general lighting. However, those spaces are air conditioned, so you're going to have larger air conditioned floor areas than the lighting floor areas. So for this, you want to work out what the square meters are for the workspace within the office there. So we've got our total lumens required, and then we can decide, okay, do we want 30 light fittings? Do we want 50 light fittings? That's a choice for you. But you'll get a figure of how many lumens each light. And from our floor plans, we can also work out what our air-conditioned space should be. So once again, we've got this caveat. A specialist should always be consulted as the type and size of the system will also depend on many factors, including the size of the room, the number of occupants, the climate of the building location, the building fabric or floor insulation, and ceiling height. And also possibly use of the building as well. How often doors are to be opened. Retail space will operate very differently from an office space in that regard. So there's many factors that come to play into it, but we can do a very simple exercise for the purposes of this assignment to get a bit of an idea about it. So generally the size of the system is quantified by the output energy. A very general guide is approximately 140 watts per square metre of the space conditioned. So we need output energy of the air conditioning units at 140 watts per square metre. To determine output energy required for an office space using a guide of 140 watts per square metre, we just simply multiply 250 square metres by 140 watts. That gives us 35,000 watts or 35 kilowatt output energy required. This energy is not the amount of energy required to operate the system. The energy required to operate the system is referred to as input energy. So much like our light globe there, just draw a simple box for our air conditioner. So our AC is our input energy, which let's say that's 2 kilowatts input energy, and then output energy in air conditioning. If it's an efficient system, let's say 3.5 kilowatts of output air conditioning power. Oh, 2, yeah, sorry. Dead, I think I might grab one. So the energy is not the amount of energy required to operate the system. The energy required to operate the system is referred to as input energy. The bigger the difference between the input energy and the output energy, the more efficient the unit. So for a 35 kilowatt output energy unit, an efficient system will use the same amount, or for an inefficient system, will use the same amount input energy. So it'll take 35 kilowatts to run, and it puts out 35 kilowatts of cooling. An efficient system might use as little as a third of that amount for input energy. So it'll be 11.6 kilowatts to run to produce the 35 kilowatts of output. That's our efficient system. So while a specialist will consider many factors as previously mentioned, a simple assessment for suitability of a unit can be determined from the output energy. So cooling output energy of 2500 watts divided by 140 watts is 17 square meters. So this is having a look at our a Dakin FTX Z25N. So you'll notice the actual electricity consumed is much less. So our power input is 0.62 and our output is 3.6 measured in kilowatts. So that's the cooling output of this unit and the heating output of this unit. So at 2500 watts cooling output, 3600 watts heating. It can heat 25 square metres or cool 17 square metres. So based on the outcome, the Dakin unit would suit a room around 17 to 25 square metres. It's clearly not suitable for a large commercial space, but may be suitable for a small office attached to a warehouse. So 25 square metres, that's 5 metres by 5 metres. That's about half the size of this room here. So we're not going to be interested in that sort of unit, but what we have is some information in the spreadsheet about what units we can use. So computers, and this is going to require a bit more research on your behalf. And looking at energy efficient computers, what is the most energy efficient way of running a computer and having, so let's say we've got dual screens, etc. So have a dig around, see.
The cafe grade sheets.
Eyes in the screens. Yeah. So you have energy efficient screens, but you also have energy efficient computers as well. I won't give you the answer what type of computer is the most efficient, but you probably come up with that with a bit of digging around.
So when you say computer, does that apply to both laptops and desktop?
Yes, exactly. Yeah. So it could be desktop unit, it could be laptop, or it could be a server unit with various connections. And also things, let's say I've got a laptop. I've got my laptop here. If it's just sitting there doing nothing, or maybe a bit of Facebook or something like that, it's using very little energy. But if I'm doing some online gaming with some intense graphics, and I've got sound and so on, it's using a lot of energy. So that same computer, for its different uses, can be using different amounts, different kilowatts. And typically the usage of kilowatts expressed on that computer is as, okay, these are the kilowatts for standby, these are the kilowatts for standard operating, these are the kilowatts for when the hard drive is being used to run. So it is difficult to compare between units because it does depend on how many kilowatts they're using for what task. But as a general rule, you can get an average kilowatt usage for units, and that's how you'll have to compare it. So power consumption by computers will vary greatly depending on many factors, depending on the graphics used. I've just settled this, I think. One of the biggest savings made. Workers shut down or hibernate their computers before leaving work so they don't consume power when not in use. Refrigerators. So we've also got a couple of refrigerators within this office space. So power consumption of refrigerators and freezers is not simply based on their initial power, climate, and unit. Factors which affect power consumption include the quality of the insulation of materials used, seals, compressors, and other components. Consequently, as refrigerators are on all day, every day, the annual energy consumption of the product is expressed as kilowatt hours per annum. So refrigerators are compared by their size, measured in litres. Similar size units should be compared unless the decision to choose a smaller fridge is possible. Solar panels, and on that one, no, we don't have the link. So for choosing a refrigerator, further on there's a link to a site that compares refrigerators to find what the most efficient for a certain size is. If you're asked to use a 500 litre refrigerator, I can't remember whether it has a freezer unit or not. I think it's maybe without freezer unit. So 500 litre, find the most efficient model and tell us what the annual kilowatts kilowatts per annum are and punch that into the spreadsheet. So solar panels have the capacity to convert direct sunlight into electrical energy. The chart indicates one panel, well, I'll just skip to the bottom here to make a bit more sense of this. So one panel can generate around 200 watts, which equates to 0.8 kilowatts in Adelaide per day. So it may be a certain wattage of panel, but given sun angles, time of sun, and efficiency of panels, we get different measures of kilowatt hours produced for that same panel for different locations. So Adelaide, surprisingly, gets less sun than Alice Springs, but a little bit more than Brisbane, but less than Geraldton and Oodnadatta. So solar panel system has 1 kilowatt on average, generate 4 kilowatt hours. For Adelaide, so 4.03. And also it will generate more in summer and less in winter. That's, I guess, goes without saying. But the 4 kilowatt hour per day is the average. The one panel can generally generate around 200 watts, which equates to 0.8 kilowatt hours in Adelaide per day. Bit of information about grid systems and standalone systems. So, connected to the grid in a metropolitan area, solar systems are often connected to the main electricity grid. This means any unused electricity goes to the main system. Power is available continuously, except in the case of blackout where the whole system shuts down. Also, it's important to avoid overshading the system by surrounding trees and buildings. Even partial shade can compromise the operation of the entire system. So it depends on how the system is wired up. There are some solar panels, they're more expensive of course, that have their own inverters. So an inverter per solar panel, they're actually produced in South Australia here. So with those panels, because they've each got their own inverter, so that's converting the sunlight from, I think it's in direct current to alternating current, or a bit more about that than I do. But anyhow, it inverts that, or changes the power that comes out. When you have inverters for each panel, then you can have some of your panels shaded, some of them in the sun, and the ones in the sun will be producing electricity. But when you've got your whole array, and that whole array is plugged into the one inverter, you can have a little bit in the shade, and that means all of your panels aren't producing any electricity. So that if you have a solar panel system where you do get lots of shading from trees and things like that throughout the day, it may be best to go with a system that has its own little inverters within the panels. Or if you get big blocks of sunlight throughout the whole day, we might as well go for a cheaper system that has just the one inverter on the wall, and I'll go through that. So that's grid connected photovoltaics. And standalone, generally used in remote areas where there aren't any power lines, to a standalone system is required. Batteries are required to store excess energy for use in the evening and on cloudy days. While this system is not affected by blackouts and is not connected to the main system, it is finite. Once the batteries are spent, only more sunlight will replenish them, unless you have a backup generator. Batteries have generally been very expensive, so this option is more common for farmers. But the innovation in battery technologies may see an increase in standalone systems for new and existing suburban dwellings. Another thing, and we don't have that in here, is probably the hybrid of those two, which is a grid-connected battery system. And it's probably what, once batteries get cheap enough, we'll probably start seeing a lot of those systems about. And if I were to be putting in a solar panel, an array at the moment with an inverter, I'd want to have an inverter that can be used for battery storage as well as grid connection to to future-proof that. So once batteries get and they're not that far off, once they get a little bit cheaper, it's going to be worth people's while to be having their systems charge up batteries enough to supply them with power for the night time, and then and any excess power they produce once the batteries are full gets sold off to the grid. That means and people will start doing that because the feed-in tariffs you get, the amount of money for selling your power to the grid is not nearly as much as what you have to buy it back for. So it's yeah. Well, you're selling it to the general community, but what are the feed-in tariffs? Does anybody know? I thought it was much lower than that. I thought it was like 9 cents a kilowatt hour or something.
9 cents.
Yeah.
Yeah, I'm not sure what rebates go. Like mine have.
Yeah. So how much are they? Like how much do they charge?
So peak about 30 cents a kilowatt hour. 30 cents. Yeah. Because we have a privatised system, the infrastructure suppliers want to make money so SA Power Networks, the ones that provide the poles and wires, they want to make money. The power retailers, so the people who own the generators, produce electricity and sell it off, they want to make money as well. And so because there are costs in generating and maintaining a system, and they still want to make money, they will sell it to us for 30 cents a kilowatt, but they'll only buy it for 11 cents a kilowatt. And that's why. But that's why these hybrid systems are probably not too far in the future, where people are grid connected, so they can use grid power when they've got nothing left with the battery. So they have the convenience of grid power, but they're not selling their power off for 9 cents during the day and buying it for 30 cents at night.
I think the feed-in tariffs they differ a lot depending on what contract.
Yes.
Yeah.
Yeah.
So if you
they do.
did it recently, they won't be as high.
Yeah.
I think when we did it, it was one of the first time we had the rebates. We did it right at the end, and then you still get 40 cents.
Yeah, that's.
But that lasts 3 years.
No, it lasts for about 20 years or something.
Well, so that's amazing getting into that. Yeah. Yeah, but you're limited.
A long time. We're still good.
The government did the really good feed-ins go for that dies off.
Yeah.
Go to the basic 9 cents.
Yeah.
But for anybody getting in at the moment, you don't have access.
No, it depends on which energy company you're with as well. Yeah. Everybody offers different feed-in tariffs.
Yeah, and there are also entities that provide the service of funding the solar panels on your roof, and they get the excess electricity that you don't use in your household. And so there are companies out there that do that as well. So for that rental space, or so for people who are renting, they don't want to be paying electricity bills. There's that option as well.
It's just more and more reason for that.
Yeah, but I see it's not too far down the future until people will be able to be in charge of where they're selling their power to and who they're selling to. So individuals will be able to be retailers as well. That might not happen. The power companies might stop that from happening, but the technology is probably there already to have Wi-Fi connected inverters that, from your phone you can go, I want to sell my stuff to this one, and switch and choose. I think the technology's there, but we'll see that soon. I'm not sure. It's a possibility. Anyhow, so working through all of that, so we've got our information on photovoltaics and refrigerators, etc., and light globes. We get down here to our Excel spreadsheet. So there's a calculator on the Moodle site already loaded with formulas for the first part of this task. Fill in the yellow squares to complete the calculator. Air conditioning. What is the floor area of the conditioned space? So we've worked that out, and we've plugged that in there. So we've put in our square metres, so for both, it's going to be the same. So is that 240 square metres, 250? I don't know, but it's somewhere around that. So we put that figure in there. Computers, generally not a particular product. What could be the lowest power requirement of a computer? And this is just average use, so average kilowatt hours. And so they've got a watt rating for our inefficient computers. Let's find an efficient computer that might be, say, 40 watts or something like that. Lighting fittings for the office. Choose an efficient office light fitting. So we've gone through and done our calculations on how many lumens we require. So here, for our inefficient, so let's use incandescent globes. So we'll go, we need lots of those incandescent globes because they don't produce that many lumens. So we work out, okay, lumens required, 125,000. Divide that by, let's say 125 per 100 watt fitting. I'm just pulling things out of the air there. So we get to our number there, and then we put in 100 here for our watts, and we get an astronomical figure at the end for that. Or we look at how many low watt LEDs we can get away with in that space, and then put in the watts of those. Then light fittings for amenities. Choose an efficient light fitting for the toilets and airlock. So in this one, the high energy, it's already put in. So you've got 100 watt incandescent globes. Find a light fitting that will produce about the same amount of lumens as a 100 watt incandescent globe, but is an LED, and let's say it uses 19 watts. And so plug 19 into there. The refrigerators, choose a 500 litre fridge of 5-star or above. So see what we can find. Now, I'm not sure if there is actually a 500 litre on that calculator at the moment. It changes all the time. If there doesn't happen to be, choose something that's around 500 litres. Maybe go a little bit larger. And then, so here's the watt rating of our old one. But we've had a look on the site and we find a watt rating for the new efficient one. Put that in there, and so that's the first part of that energy calculator done. Like that. This is the link to the site for your refrigerators. It doesn't work, unfortunately, here from using these slides as a PDF, so we'll keep cruising past. But at home, that should work.
Your control panels.
Yeah, okay. Oh, for scrolling up and down.
Get out, hover over it.
Look, yeah, we don't need to go. That's something that you can go into at home anyhow with choosing your refrigerators. Because if I go into it and I'm mucking around with it, I'm going to give you the answer straight away.
It's only 5.
Give us a carrot for coming.
Oh, it's like unwrapping your presents on December 24th, mate. Just no, it's simple. It's easy. Yeah. So for the office building to provide 250 watts, and so this we've already worked through. So choose an energy efficient light fitting for the office. Determine the lumens per light fitting. How many light fittings do you need to achieve that 125,000 lumens, or what is that figure that you calculate yourself? And this gives an example of that. And then in this example, lumens indicated. Also, this is about your different light fittings. So we go through that at home, and amenities, lighting, your information is there. But basically, there will be 21 lights for the amenities, and that's already in the Excel spreadsheet. and this is what I went through earlier. So the Excel calculator will let you know how many solar panels will be ideal, but how many will actually fit on the roof. So we go through that exercise of working out how many panels we can get on there. Be sure to leave at least 600mm space around edges between each 2 rows of panels made. So there, that's what we're doing. And that's it for the explanation of the energy component of the assignment. Now so that is the big chunk of the assignment, really. So the rest.
So
Yeah.
can we just go in Revit and puzzle with the cells there? Is that the idea?
So you can. Do you have Revit at home?
Yeah.
All right. Well then, yeah. Then there is. I don't think I've taken.
So
I haven't taken it off. Or task 3 commercial. Oh, it's all grayed out. I don't know why that's grayed out.
I'm not sure if I'm
Oh no, it is grayed. So what happened last semester was many students didn't have Revit themselves at home. So if I was to be providing them with the Revit file for this, because I don't have Revit either, and I don't use Revit myself, I use AutoCAD. But no, I don't think I am. I've mucked around Revit here.
So everybody
But
is
anyhow.
a fair of an equal chance.
What's that? Yeah, well,
Yeah.
so if I was to include these Revit files on there, because they differ from the assignment drawings. So these are the assignment drawings that I put up there. So our office space. But this batch of Revit files, that's for the old building. And so previously, the assignment just included a Revit file, but because lots of students didn't actually have Revit at home, they couldn't do it. So we can't do that. So we had to put up a PDF. Now, also the Revit file, the building in there wasn't very good, so we choose a better building. Hence, you have to do it manually, but you can also just draw. I don't know how you do it in Revit, but if this was in AutoCAD, I'd get the assignment 3 drawings. I'd grab that roof plan, put it in as a PDF, underlay, scale it up to be the right size, trace around the inside of the parapet wall. There we go. And then I'd create a little block that's 750 by 1500, and then muck around with that. So it'll take me 2 or 3 minutes to do that. And possibly it's the same process in Revit to do that. So, and I'll just quickly show you the energy calculator again. So open that in Excel. So that's the bit we've seen. Then under that, you've got, try to increase the size of that. Let's go to the screen. We've got our, so that gives us the number of panels we need. So we have a calculator here for how many panels would it take for solar panels to pay for themselves. So you've got got your old electricity use or your low energy electricity use, and you can calculate that for both scenarios.
So it doesn't mean that whatever figure we have on the calculation of the electricity on that top table,
Yeah.
we compare it to the solar panel.
Yeah, so it will then work out in both scenarios how many solar panels you need. So this one, because there's enough numbers put into this one already, it tells us we need 341 solar panels to produce the energy that's required to run that office building with the old, the inefficient appliances. We can punch all the numbers in here for our efficient. What we can do is just go put in a 2 there like that. That already gives us a bit of a. So we're using $48 of electricity a year. actually, I didn't put it in large enough figure for that to give me. So we need 17 panels. But yeah, anyhow, so you'll fill this in and it'll tell you how many panels you need, and then what the total cost of that setup is going to be. So for our inefficient appliances, there we're going to have to spend $136,500 on the solar panel setup to power that. Now this is for an office building, of course. But yeah, you get your
what calculation are we putting in the yellow column there?
So
if we have 17, if we have 17 panels of the solar panel,
yeah.
So what would then be on the?
So that's a great question. That's fairly simple. So that's our total cost of the panels there. So for the inefficient system, we've got our total cost. Now this is our cost per year of electricity use.
Yeah.
We can divide that $136,000 by 49,151 per annum, and that will give us how many years it will take for those solar panels to pay for themselves. So that's going to be a little under 3 years. So 3 years of spending $49,000 on electricity. It's better to buy an array of solar panels that cost $136,000 than to spend that for.
You could just give us the answer.
Well, I can, but that answer's going to change. So the answer as it is. So if I get to the calculator bit on my phone, there we go. 130. So 136,505 divided by 49,191. 49,191 equals 2.7 years to pay for itself. So that's the way it's calculated. So how many years would it take solar panels to pay for themselves? Yeah. What's that? Could do, but it's super simple to calculate yourself. Yeah, and then in your assignment, just tell me how many solar panels you've been able to fit on the roof. You're probably not going to be able to. In fact, I know you're not going to get 341 panels on there. So if you're running the inefficient appliances, air conditioning and so on, or you're going to be buying power off the grid anyhow. Put a 0 back in there, just in case. Shut that down. Don't want to save it. So that is assignment 3. Do you guys still want me to rush through assignment 2?
Yeah, I don't mind the servicing.
Yeah.
It's just the same process with the assignment 3.
No, assignment 2 is much easier. So with assignment 2, it's about choosing an air conditioning system. And so we'll go in there. We'll just go have a look at services just quickly for assignment 2. So down here under heating, cooling. Oh, that's the home website. I'll have to look here. Compare the advantages and disadvantages of different air conditioning services. Make a recommendation to your client based on your research and indicate the location of the service on the level 1 floor plan. Yeah. So what we don't have there is actually a link for comparing air conditioning services. That's something that you're going to have to do your own research on. So think about the various different services, the air conditioning services that can be provided, be it a ducted air conditioning service where we have maybe a refrigerated unit which has ducts to each of the units, or do we put in split systems to each unit, or do we have a ducted system with a ground source heat pump, or do we there's a Sealy brand of air conditioner that uses an air source heat pump. Do we go with that? So do your research on what system is going to be the most efficient, and what is also going to be cheap to install, and what is going to be user friendly as well. So individual air conditioning and heating units for each unit, that's probably going to be the most user friendly, because it gives the people the rapid heating and cooling for their units, rather than having a shared system, which you then have different climate controls for your different zones. Yeah.
So if we are talking between a split unit and evaporative system.
Yes, so you can have an evaporative cooler.
Yeah.
You can have a the names I used just before. A refrigerated, so an evaporative system, a refrigerated unit, or a reverse cycle air conditioning unit, or a split system unit where you have compressor outside, condenser inside.
So can you choose two, or is it a comparison?
No, it's so compare the advantages and disadvantages of different air conditioning services. So find a few of them and talk about them.
Oh, you have to be more than two.
No, you can just do two if you want. That's fine. It's one of those things you get out what you put in. You can go think about it. Okay, all these other units, they're just really not going to be they're not applicable to this situation. I won't even talk about them or analyse them. Think about the ones that are most pertinent to the situation. Talk about them, but basically you have to compare advantages and disadvantages of different air conditioning services. So these plural.
I was looking up geothermal HVAC, or how do you pronounce it?
Yeah.
But that would not be suitable for this. So I can quickly say, oh well, that's going to be way too expensive.
Yeah, because we've got four units.
Yeah.
And and to drill 15 kilometres into the Earth's crust.
It's very interesting.
Yes. Yeah.
So if you've got that split system, you don't need ducting.
No, you don't need ducting. So you can have a split system with ducting, but in this scenario you wouldn't, because because
Michael, the English is that a unit is just 30 square meter unit.
yes,
Do you have any options? Go for that. The operating pool or anything? Yes, probably a split system is suitable for them.
yeah.
Really small one.
That's what I think. That's that I think is, without giving the answers away. I agree with you. So that Dakin unit which we spoke about there, that will do 25 square metres. Yeah, it's probably going to be your choice. And that's it.
So does that mean that we talk about the construction details as well?
Oh, yeah. So that construction details. You don't have to put construction details into your assignments, but it just makes them better if you do. So it's good to grab details from the product manufacturers and put them in there. So if you're saying, oh look, we want to do this this heating power panel wall, grab the details about the heating power panel wall and put them into your assignment, saying this is what heating is and this is how it's put in. So it helps give you some context to what you're writing about. So you write about it and then you put in the pictures. Yeah. So so what I wrote here is just say where pertinent, include structural details of the building systems chosen. So wherever you think is a good idea, put them in. Yeah. Well, yeah. Yep. Yeah. So that's it for assignment 2. Yeah. Yeah. That's
I've
fine.
got a 3:50 wake up
I've got a 4 o'clock wake up tomorrow.
I'm gonna catch a plane. So if I miss the plane, doesn't matter.
Well, I've got to drive to Lyndhurst.
I'll wait till you from a little plane.
Alright.
I'll be shitting myself on
Yeah.
the plane. I've never been on a little plane before.
Yeah. I had fun.
Yeah, it's gonna be a hard day. A really hard day. I'm testing at the end of this week.
Yeah.
Hopefully I'll fail it so I don't get that job. Sounds exciting. Anyway, good luck.
Enjoy. Yeah.
I'll
Yeah. Good luck to you too.
safe trip
Will do.
from gold and uranium, silver, copper. Thank you.
So that's it for the assignments. Unless anybody has any further questions for assignment 2 and 3. Very good. Alright, so then tonight we're going to finish off the glazing and cladding section. So get into glazing. So for our commercial glazing, we're looking at primarily curtain wall glazing. So that's things like this, where we have large sections of glass to encase a building and enclose a building. Obviously, there are issues with curtain wall glazing. There's a lot of heat transmitted. Heat coming in, heat going out. There's less control. But what you do have is you have lovely light office spaces, and you do have attractive building facades. So glazing in commercial buildings come in many forms. Styles sometimes associated with glazing are frameless. So that's not frameless. It's got the frames, but we'll see some frameless stuff in the slides here. Storefront glazing. So that's typically this type of glazing is used for storefront, where we've got these 50mm commercial frames that hold glass. It's a little bit more robust and it's cheaper to produce. Curtain wall, so that's where we have large areas of glazing extending from the floor to the ceiling. Partitions, so we can have glazed partitions, so between office spaces that allow for light to transfer, but minimises or cuts down on some of the noise being transmitted. Slump glazing or slump glass, that's where you do things like that. So you get a bit of glass and you put it in a kiln and you put it on top of something for it to melt over that, and then let it cool, and you can pull out your funky shaped vanity or so from that. So all sorts of things you can do with glass in that fashion. Toughened glass. So does anybody know what toughened glass is and how do we get to toughened glass?
Does it have like a little metal wires in between, or?
No, that's not toughened glass, but that is.
Windows
What's that?
Windows screen on the car.
Oh yes, that's toughened glass. Yes, yeah. And for anybody who's broken a windscreen before or broken a window in a car, you notice it breaks into tiny little pieces.
Yeah.
So, but it is actually stronger than your standard float glass. Like when you break float glass is quite easy to break, and when you break it, it breaks into long shards, like large shards like this. The reason that well, toughened glass is made from float glass. So initially you get your piece of float glass and you put it on this bed for being heated. It's brought up to, I think it's around 1200 or 1300 degrees Celsius, so it's brought up to heat, and then it's cooled rapidly. So so you've got your float glass, and bringing it up to heat again energizes the particles in there, and they can start to form bonds. But then the rapid cooling of it means that it forms tiny little cracks in there, like little stress points. So the heating of it and the cooling of it actually makes the glass stronger. So you've got your initial float glass, and you heat it up and then cool it, and that makes it stronger once again because it forms bonds. But the rate at which you cool it means that it will break into tiny little pieces when it does break. So that's how toughened glass is made. The type of glass you're talking about with the mesh in it is known as laminated glass. So it's where you've got a piece of just your standard float glass, and then you put some mesh on there, and another piece of your float glass, and then you heat it up again to slump around the mesh. And so the mesh becomes part of that glass, because the glass molds around that mesh. And that glass, is, well, it's good for security. You can't break through it. But the more modern way of doing that is, in your laminated glass, is to have I think it's polyethylene film, so a clear film that goes between the two layers of glass, and I think it doesn't need to be heated up again. I think you just get your glass, you've got your film on there, and another piece of glass on top, and when you go to break that glass, the polyethylene film stops that glass from breaking. It'll still break into these pointy shards like standard float glass, but you won't be able to break through it because it's quite tough. It's flexible, it will stretch. The toughened glass, that's the glass like for your windscreen. But also you'd use that in a building situation for glazing under 400 millimeters in height. So for bushfire areas, you have to have toughened glass for the first 400 millimeters of your glazing if you've got glass at floor level. But it's a good idea to use toughened glass down there anyhow for kids, whatever, zooming around in little cars and things like that. Just because it is much harder to break, and then when it does break, it's not really dangerous. It's less dangerous.
Vacuuming.
Vacuuming, yeah, exactly. If you got one of those big cast iron cleaners.
The tempered glass is the same?
I think so, but it is. So tempered is another name for toughened, or the tempering process is the way of creating the toughened. I think that is correct.
So is it the same glass they use for most, like maybe aquariums and other stuff?
I don't know, but I assume so. Yeah, I don't know. I guess I don't know actually. I don't know what sort of glass you would want to use to hold that head pressure of water. That is a very specialised thing. But I don't know. But I probably want to use laminated glass for aquariums. Because you'd think that laminated glass would have a higher tensile strength than toughened glass, but that's just an assumption. Because that tensile strength is what you'd want in the aquarium situation. Self-cleaning glass. Has anybody come across self-cleaning glass before?
It's got a film on it from bacteria and membranes on it. It cleans itself.
Yeah.
It's super expensive.
Yes.
So you're not going to get it in residential stuff, but for skyscrapers, it's going to save you in cleaning costs, obviously, and take your money, so it might be worth it.
Yes, exactly. Yeah. And so, and also it's hydrophilic, or no, hydrophobic. I know, but it means water doesn't bead on there. The water sheds off as well. So that film Yeah, so that film, has the bacteria, like you're saying, that breaks down any organic material that lands on the glass. So bird books or whatever, it gets broken down into tiny little bits. And then when it rains, the rain carries those tiny little bits away, but the rain doesn't stay on the glass. It just falls away. And spandrel, spandrel is a term to describe any floating building element that goes between two supports. So in this scenario, we're probably talking about a large glazed unit that would go between two points of support elevated up, like a portion of curtain glazing wall. Or it could be a dividing panel between two elements. So curtain wall is a non-load bearing exterior glazing system used to create the exterior skin of a building. So that's where we would have all the load bearing done by an internal structure, for example, and then wrap the building in glazing that is non-load bearing. And there are several different ways of doing that. One of the ways of doing it is with our traditional framing. So I guess this is not really curtain. This is not typically what I would say is curtain wall glazing, but close enough. Same sort of principles apply. So here we have the storefront type framing there. So that's exactly what we're seeing here. The storefront aluminium and glass framing system typically used at ground floor locations of commercial buildings. So the difference between the two is a curtain wall, multi-span locations, high design pressures because we get wind acting on the side of the buildings, and as we get higher, we can have more wind acting on the side, and also with this type of system we have our mullions going from floor, from point of support to point of support, and we've got those at every 900 millimetres or so there. So that glass isn't going to be taking a huge amount of pressure per mullion. So those mullions are taking all that pressure, whereas a typical curtain glazing scenario, we would have much smaller frames than that, and they'd be much further apart. So we have to have higher design pressures. Typically more than 3 metres high, and there are all sorts of different custom design features. Storefront, single span, typically less than 3 metres tall, economical system, slim system depth, and erected and glazed on site. Storefront components, so the head is the horizontal frame member which forms the top of the frame. So for ours, that's this bit right up the top here. Maybe some of you can see it, maybe you can't. So that's our head. So the sill is the bottom horizontal framing member. Jamb are these outer portions. So essentially that one right at the end is the jamb, and the one right at the end up there is the jamb. And then all the internal ones are our mullions, so a vertical framing member is separating the fixed lights from the glass. Pressure plate is an exterior extrusion that is, so when we talk about extrusion, it's extruded aluminium. So it's a piece of aluminium that has been extruded. An exterior extrusion that is mechanically fastened to hold the glass in place in curtain wall applications. Cover is a finished snap-on piece at the exterior of the building applied to the pressure plate. So you get the pressure plate there, but typically the pressure plate is not visually attractive, and so a little capping is pressed onto the outside. If you were to cut through these aluminium frames, this is typically what you would see, a profile similar to that. So normally we don't get to see any of that stuff. We just see this face here, which is a nice clean face, and we'll see this face here, or that face there, which is a nice clean face. That's what we see. But inside of here, we have these things going on. So our accommodations for the glass. Then we also have these little channels here And those little channels are for fixing them together. So those screws go straight through that mullion, and they will screw straight into that head. There, like that. Those little channels in there.
What are the other channels for? They're sort of in their square.
These channels here.
Yeah.
They are to take pieces of rubber will squeeze into there, and those pieces of rubber have little, they're shaped like this. So we've got our piece like that, and then they will go like that. And so they'll fit. So this is our frame. They'll fit into our frame. Well, actually, our frame goes like that, and then over this way and up there. And our piece of glass fits in here. When the piece of glass fits in there, it squashes that point down to keep that under pressure all the time. So it's always, so for the rest of its life, it's being bent back and it's pushing against the glass, creating that seal. So that's, if you wanted to have a look.
Yeah. Plastic.
Yeah. These ones have got mastic in there, but that's what those channels are for, is for accommodating rubber. Possibly your frames will have to be steel reinforced, so steel channel or tube needs to be stabilised. To stabilise the mullion in certain conditions, it can be used with curtain wall or storefront. A subsill is an outlet for water that is used at the sill of a storefront frame. So when we get water coming down here and collecting here, we want to ensure that all of that water goes outside and none of it goes inside. So we have a higher lip on the inside, a lower lip on the outside, and then we have drain holes as well to ensure that water goes outside, or weep holes, sorry. The weep holes, the hole in the system, allows water to drain. So curtain wall variations, we've got SSG, which is structural silicon glazed. So you're starting to see a lot more structural silicon used around the place because it's a fantastic way of just, quickly sticking stuff on. And with, electrical, battery-powered silicon guns, you can get very nice even beads of mastic or silicon, which is fantastic for sticking things on. So that's structural silicon glazed, inside set, or stick built and unitized. So that we'll go through those other ones as we went through. So conventional curtain wall, a stick built system utilizing pressure plates. So that's like what we saw up here with our pressure plates. A curtain wall, a factory glazed system installed, unitized curtain wall, a factory glazed system installed in large units. And structural silicon glaze has silicon beading or butt glazing to the structural or to our mullions there. Mullions that are specifically for butt glazing or structural silicon glazing. There's our plan view of that. So we have our beads of mastic and silicon. The glass just goes straight onto that. Then we'll have a backing rod in there, and then silicon on the outside, or our backing bead in there. And we have two panes of glass here with a mastic seal between them. That they're known as insulated glass units, or IGUs. So that's how we do double glazing. That's the modern way of doing double glazing. So this is the inside glaze system typically used to eliminate working on the exterior side of the building. So we have mullions, and then we can put the glass into those mullions, and then we can apply those fixing plates, and then we move on to the next window, etc. So we're not having to work on the outside of a building, which can be very expensive. This way, it's much cheaper and easier to install, but we don't get quite the wow factor with this system as we would get with the structural silicon glazed system, for example. So water and wind issues, so quality installation is critical, so that just goes for everything in building in regards to water. This includes anchorage and proper sealing of the system. Water will at some point penetrate the exterior of these systems, so you need to have systems in place for getting rid of that water for when it does breach the curtain wall glazing. It's a rain screen, the exposed outer skin or surface element of the wall, backed by an airspace designed to shield the joints from water. So we have our rain happening on here, we have our initial seal, and that's the way that the rain screen works. But, we'll go on to the next slide. That will possibly at some point be compromised. We've got wind and sunlight and heat onto these rubber seals all the time. And so this area under here is the area that's allowed to get wet. So when that seal is compromised, then water makes its way down into here. And that's why we have weep holes where the water can flow out into that exterior capping on the pressure plate. And then that has weep holes in that so the water can flow out of there. So even when this rubber deteriorates on the outside, we get some bits of water, it's all directed outside once again. This seal on the inside of the building is critical. So if that seal gets compromised and you get a lot of wind pressure from this side of the window, that means that this area can become pressurized and push water inside the building, which is what you don't want. So the equal pressure and rain screen allows gravity to take the water out of the weep holes. If the chamber was not equal, the water would permeate. So basically, if that seal becomes compromised, well, then the pressure out here is going to be greater. Well, the pressure out here is always greater than the inside of the building, but if it gets compromised, the water will flush. Or if our weep hole becomes blocked, then we can get greater pressure happening in here, and that will end up helping that seal become compromised. So seal in this area degrades and weeping occurs, thus moisture in the internal area of the horizon. So weep holes hold the system allows water to drain. So 2 weep holes required per light glazing. For your horizontal joints, to fill in those gaps there, use joint plugs. So if you do get any water traversing down here, it's sealed from going into those horizontals. And also at the top, to help disperse water before it wants to start coming down the framing, you've got mullion caps, top and the bottom. So to ensure continuous improvement bead sealant. So glass will deflect under pressure, and so glazing and framing needs to be designed to accommodate or control that deflection, so the amount of inward and outward movement of the assembly when wind pressure is applied. Wind load anchor allows for movement due to expansion or contraction and live load deflection of the floor slab, but remains fixed because we've got elliptical holes here that are now allow some movement. So that's the same as your truss fixings on top of your internal non-load bearing walls, for example. Also on top of your framing, you've got 2 different anchors. So you've got the T anchors on the inside and your F anchors on the jambs. Curtain wall is a flexible system designed to accommodate the vision of the design professional. So there's all sorts of things you can do with that, and I'll show you a few. Well, there's a few fantastic curtain wall glazings in and around Adelaide. I've got them, some of them up here afterwards. So curtain wall is designed for use in multi-span applications. So it can go all the way up the side of the building, not just from floor to ceiling. storefront is also a flexible system, but it has limitations due to its nature of design. So that is the slides in regards to curtain wall glazing. What? Have a look at this dude. Get rid of that. Get rid of that, and we want to bring this over here. So that one, oh yes. So the Samory building is, does everybody know this building on North Terrace? So that's, so this is, what's that? Yeah, so what did you want to know?
Over.
Over?
Yeah.
The oval is saying.
Oh, the oval.
Not that one, I think.
No,
Not
this,
that one.
no.
Yeah. This one is
It's next to
different.
the Enrise, next to the
Yes, yeah. So it's on North Terrace, across the road from the City West University of South Australia campus. So that's City West campus just there in the background. So this is North Terrace running down here. That white ute there is driving to North Terrace. So this is a very, very new building. I think it's awesome myself. So that's it from another perspective. That is curtain wall glazing. It's, I guess, essentially they're using what we would refer to in this lecture as storefront glazing. So we've got our frames, but what they've incorporated in their curtain wall glazing are shading caps over the top of those triangles to provide the right amount of shading for that elevation. So to maximise or to make it more solar passive design, still enable that curtain wall glazing to get lots of light in there for use during the daytime, and it ends up being a beautiful looking building for that.
Michael, is there a gap between the curtain wall and the building?
There is,
Yeah.
yeah. So on some of the floors, I think go right up to. I haven't been in it myself either. I've just looked at pictures. I should take a wander around in there sometime. But you do have void areas in around that base. Yeah. But then I think further up we've got floor areas going right to the windows. Possibly we've got some more photographs to show that bit better. So that's on the western elevation. So there's a lot of those shading caps over there on the western elevation. There are floor areas. Well, we can't see whether that floor area goes right to the edge. No, I don't know actually. But typically with curtain wall glazing, you do have floors going right to the glazing, or in many situations.
So here, it looks like here, there's a gap where the bridge is.
Yeah.
The floor is not going to glazing, but further up, it might touch.
Yeah.
Yes, the gap.
Bottom floor shows clearly.
What's that?
Bottom floor shows clearly.
Yeah, there's a gap. See, there's a void between the glass and that's a void there.
So I also expect when you see the rooms with the colors, that's probably where it's touching the glazing. Further down, you've got openings. That's my guess.
Yeah. Maybe. Yeah, it'd be good to do a site visit, wouldn't it? And have a look. I don't think this is ground floor. No.
Yeah.
Well, there we go. So we've got flooring going straight up to the glazed portion, but in that, from where we do have floor going straight up to the glazed portion, we've actually got solid aluminium infills instead of the glazing. So possibly we can look at that and go where we have some solid infill. So we've got solid infill happening here, around there. Maybe that tells us. Anyhow, it gives us some insight. But another interesting thing is the window legend for the building. So because it's made up of many thousands of windows, they've had to do a window legend like this. So they've got, what is it, 1, 2, 3, 4, 5, 6, 7, 8 types, and they've given each type a colour code, and then they've just colour coded onto the building elevations or the axonometric drawings there to go, this is the type of window we want here, and here, and here, and here. So that's their window legend. So I think they're really, really very clever way of making such a complex building. So that's a fantastic version of incidents of curtain wall glazing. Another great one, I think, is the SA Water building on Victoria Square. Unfortunately, this site doesn't show the curtain wall glazing all that well. But the concept there is, okay, being SA Water, they wanted something that looked like water, it gave off that feel, and so they've got toned glass here in various different tones and shades of blue and aqua to create that sense of water, and then large sections of curtain wall glazing at the bottom floor. And this one has actually got glazed mullions. It's very hard to see, but can you see this little strip here? There, that's a slightly different colour as you're looking through that. That is a glazed mullion. And so rather than have an aluminium mullion there, we have a plate of glass, and that is fixed onto the glass. I've got another picture here. This one shows glazed mullions. Or I'll go back. No, I won't go back. So that, yeah, probably be a little larger.
We saw something similar last week when we were having that.
Oh yes, with the squash courts.
Yes.
Yeah, that's got glazed mullions there, does it?
Yes, it does.
Yeah. Yeah. So that's another way of having less obtrusion in the framing. So it provides strength for racking forces, for the wind pushing against it. And these fixings are what are known as spider fixings. So this detail relies upon holes being cut in the glass, so hole drilled. So that'll be done in the factory, and so they're done in specified locations. And then you have those spider fixings fixed to these glazed mullions there, and they've got their little chrome end caps on them, etc. And then you have silicon joining between mullions and the glass. And another, see if I can bring up that one. This is another system of essentially mullions that are set back from the glazing. So we have steel tubing with standoff brackets to our spider fixings, and then to create additional strength to that steel tubing, there is a stainless steel wire that runs at the back of that to pull it all into tension. So this is working like a truss. Can everybody see how that works? So basically what it is a truss with the spider fixings fixed onto that truss that hold the glass. So it's another way of producing a less obtrusive framing system. So it's about minimising the amount of framing in there.
So how does the tensioning work then?
So
they're horizontal.
No, so I'll draw it up a bit better or a bit clearer if I can. So in section, we've got our pane of glass heading down there. We've got our spider fixing coming off of that, and then that goes to a standoff bracket, and then you've got your steel tube that runs down there like that. Now, if that were our only system, when we get racking forces on there, it relies upon the amount of flexure in that steel tube. To minimise that, what we can do is we can carry standoff brackets further out here, like this, and then have a steel wire that does that, and all of a sudden, by doing that, we have a truss, because this wire is in tension, and so that wire is really tight. So that wire being tight, it's putting pressure onto the back of that, because when we get wind on there, primarily it's going to be a racking force applied on the side. Yeah, yes, we will get suction at times, but not to the same extent. And so to resist those forces, we have that wire at the back there.
Is the wire going over one of these spiders at a time, or is it going over several?
In this scenario, it's going over several. We can see that it goes over 1, 2, 3. In that bit we can see, but that's just a simplified version of that. Yeah, you can go over, you can have several of them. But essentially what we have there is a truss.
Yeah.
And trusses keep popping up everywhere in construction. And another interesting one. Has anybody ever looked at the glazing on the convention centre? The old. Do you know which part of the old convention? Which is the old part of the convention centre? I'll see if I can. I'll close some of these down and give you a few more tabs. Images. So that's the new section. I'm not a fan of that bit, but the old section. So everybody knows that convention centre. So that's the view from across the Torrens. I'll see if there's any that show the glazing up close. Oh, actually, there we go. That one was not too bad. So what they've done here, which is pretty tricky with this glazing, they've got their frames running horizontal through the glazing because we can't because you need frames to help carry that. But rather than having vertical mullions, they've got cables that run up there. So we can see them only ever so faintly in this photograph. So cable running up there, and cable running up there, and so in cross section, what we've got our horizontal framing members and our glass coming off that, like that, and then cables with an adjustable nut, and then another horizontal framing member like that, adjustable nut like that. So that enables these frames to be quite small, but span really long distances between point of support to point of support, like probably 6 meters or so from point of support to point of support, because they're hanging from these cables. Those cables are just going to be in tension, and that's going to support those frames in a vertical sense. And that's another way of getting a lot of glazing, or it's another way of minimising the framing within that glazing to give that, a much clearer outlook. So that's a neat trick as well that's on display in that building. But that's it. That's yeah. It's all the all the wow bits about curtain wall glazing I know of in Adelaide. And also, because I think I've told you already last week, because next week I'm working over New South Wales, I can't put on lecture for next week. So next week is a free week to work on your assignments and get your assignments in. Seriously do that. Because you'll find things really start stacking up towards the end there if you don't. But then the following week, after next week, I'll be back to go through box gutter details and to do box gutter and rain head calculations. Because that's something which is going to be important for you as well in the future. And then from there on, it will just be working on assignments. So, thank you. Have a fantastic week.
You too.